Okay, yeah. Hello, everyone. My name is Elena Vollmer. I'm from the KIT in Germany. I'm very happy to hold this talk today. It's on a bit of a different topic than everyone else has been discussing. So my research focus lies with also image analysis, but UAV, so drone-based thermography, and that necessarily means then multispectral data. And recently I've been delving into the world of AI as well. And today I want to share a bit of my work with you, especially as a use case in the project AI for EOSC, which uses the same platform that Enoch just showed you guys as well. So I want to start off with some motivational background. So what is thermography? Because I know that a lot of you come from a different scientific background and how we can use it in the urban energy context. Then I want to just discuss two different models that can aid in urban infrastructure maintenance. One, thermal bridges on building rooftops detection, which a couple of colleagues of mine developed, and then thermal urban feature segmentation, which I've been working on. And then I just want to introduce the AI for EOS project to you and the training platform that you can use to train your models. Yeah, as a background, when we think about urban infrastructure, obviously cities, they consume the vast majority of the world's energy, and mostly these are obviously buildings, and heating accounts for almost half of the global energy use in these buildings. And heating supply, so supplying these buildings with the heating is an essential service, we can say. In light of what we can call the ongoing energy crisis, especially in Europe, it's obviously important to maintain a high efficiency and minimal losses in all of the infrastructure that's involved. And so today I just want to show you what we can do by combining different technologies. So thermography, UAVs, and AI to support in heat-related urban infrastructure. The key element here being thermography, which is a technology that allows us to measure infrared radiation, so create heat images of whatever surroundings we're inspecting. And when we combine this with unmanned aerial vehicles, we can look at the relevant infrastructure that interests us and pinpoint areas of unwanted heat loss that are otherwise invisible to the human eye. So how do we do this in practice? Well, we start off obviously with some urban infrastructure that we suspect may be potentially damaged. This can also be like generally city districts and so on. And then we organize some UAV flights, which due to the technology, it's pretty simple to do actually. So we can program the drone to fly over the areas on their own or on its own. And we thus acquire multispectral data, so RGB images you'll all be familiar with, the standard red, green, blue, but also thermal images. And we can then analyze these and identify our thermal anomalies. This is where AI comes to play. With the results, we can then repair the urban infrastructure that we're looking at. As I described in the beginning in my agenda, I want to discuss two different use cases. One of them being thermal bridges, so buildings, so the actual energy users. And so the point of this model is to find thermal bridges on building rooftops. What are thermal bridges? Well, they're weak points in usually the entire building envelope, which just allow heat to pass through more easily. And so to mitigate this, we can identify these thermal bridges and provide thus pointers to different building owners and city officials for energy retrofitting measures. The other model is with regards to energy supply. So here we're discussing district heating networks. For those of you who aren't familiar, these are quite widespread in colder regions like Northern Hemisphere, where we use underground networks of pipelines to distribute heat to end energy users. And so through a trained model, we can identify common thermal features in urban settings to use these and sort out false alarms when we're actually searching for anomalies that pertain to leakages from the pipelines that are underground. What do these problems look like when we define them in the terms of AI, while the thermal bridges on building rooftops detection would be a single class object detection problem. Actually, the annotated images are polygons, so we can also see it as an instance segmentation problem, but we're handling just one single class. And then for the thermal urban feature segmentation, we have multiple classes, as you can see. So buildings, cars, manholes, street lamps, people, and so on. And here it's sufficient to just see it as a semantic segmentation problem. I'm very thankful to the previous talks that have discussed all the basics of these different kinds of models, so I don't have to discuss these in detail. But what I want to focus on mainly is the data, actually, because I suspect that a lot of you start with different kinds of data sets, and so it's about how we can process these to actually input them into our AI models. So the data that I'm working with is, as I mentioned, multispectral. So we have the RGB and thermal images that are actually acquired with the same a dual camera. And then the UAVs flies with a high overlap. So we have a lot of overlap in our images, but otherwise there's some differences. So for the building inspection, we fly at a 45-degree pitch angle, as you can see in the example image, and during the daytime, so we can actually create height maps. I'll come to that in a moment. And then for the thermal urban feature segmentation, we fly at a 90-degree angle, so just downward facing, so we can have a closer look at the networks that are actually under the streets here, also the high overlap. And then we fly at nighttime to reduce as much thermal heat as possible. So these are our raw images that we start off with. What do we have to do to actually create our multispectral data set for AI training? Well, the images that we start with, as you can see, are quite different, even though it's from the same dual camera. The thermal images have a lot less resolution, and also the aspect ratio is different. So we have to align these in a way. So we start off with the RGBs, and we actually have to undistort these depending on the camera you might be working with. In our case, this camera had quite a lot of called fisheye distortion. And so to remove that, we experimentally determined the intrinsic camera matrix and distortion coefficients of the camera. And then to align both of these, we calculated homography matrices using matching feature points in both images. Then obviously we need some kind of annotation information. We use the software VGG image annotator, which works quite well. And in this case, so this is the pipeline for the thermal urban feature segmentation. We need segmentation masks, as was described in the first lecture of the day, presentation of the day. So we can transform our annotated polygons with our different class labels into masks, and then align these with the other inputs. So that leaves us with some annotation masks and 4-channel image inputs. Now for the building inspection, the pipeline is very similar. In this case, as I mentioned, object detection or instance segmentation, so we don't actually have to do anything besides aligning the annotations to the size of the rest of the images. But what we do is, because we have height information included in our images, due to the 45-degree angle, we can actually see the building facades and so on. And the images are acquired during the daytime, so we have a lot of information. We can use software, in this case context capture software, to create a 3D model, which in essence is just a 3D point cloud. And then we can estimate the distance between the points in 3D and 2D spaces and project them to the 2D space, so create a height map, which we then have to align to the same aspect ratio again. So this gives us, in this case, COCO-JSON annotations and 5-channel input images. What these look like in practice are exemplified here. So for the thermal bridges on building rooftops, we have the RGB, then the thermal, and then the height map. And for the thermal urban feature segmentation, we have the RGB and thermal image. And when we input these into our models, our outputs will look something like this. So we'll have, depending on the kind of model we have, instance segmentation or object detection. And then for the thermal urban feature segmentation, we have segmentation masks with our proposed predictions. Now, I mentioned the models themselves, so discussing, coming to the actual AI part, the data sets, as you can see, are quite small. This was obviously also discussed in the previous two talks. And so the models were also selected to keep that in mind. The thermal bridges on building rooftops detection is more of a model ablation study. So we have different kinds of mass RCN models with different backbones, including a SWIN transformer, and then Trident Net and feature selective anchor-free models, which are only object detection architectures. For the thermal urban feature segmentation, I selected the UNet model because it was also discussed in the first talk, interestingly, and it's a very common model for also small data sets and quite famous in the semantic segmentation world. So you can use lots of different libraries and toolboxes. There are very many different options out there. And these are the two that were selected for these two cases. Also, something that's become a lot more prevalent, especially in research in general and the scientific world, is energy monitoring. We see when we train these models, it takes up a lot of energy. So keeping track of that can be very important. There are different toolboxes you can use to do so. And then the previous talks also talked about different evaluation metrics. So here we're using different kinds depending on the problem at hand. And the thermal urban feature segmentation is a study that is still in work, where I'm focusing on actual different options of data preprocessing, different filters we can use to enhance contrast, remove effects like thermal vignetting and so on, while the thermal bridges and building rooftops detection is already a finished study, as I mentioned about model ablation. You can read up on that study in that paper. I decided not to include the whole table with all of the evaluation metrics. I can say that the SWIN transformer-based backbone mask RCNN performed best, and that also some data augmentation took place, like random flipping and so on. Exactly. What I want to discuss, though, to finish the presentation, so to speak, is the AI for EOS project, because I think this is the most relevant to a lot of you who don't necessarily have anything to do with multispectral data or drone imagery. But the project I'm working on, as Enoch mentioned, is about providing computing resources as well and services with regards to AI, deep learning, and machine learning for the European Open Science Cloud. The project itself is about enhancing the existing platform, which is the Deep Hybrid Cloud. And the project is a European project that runs until the end of 2025. And the key factors that are going to be included are additional features like federated learning and so on, but also interesting for me in particular, keeping in mind that I'm a university researcher, things like experiment tracking with MLflow and so on. You can read up on the websites. Just for a quick overview, Enoch showed this as well, but this is what the marketplace looks like. So for example, if you have some data and you just want to infer with a model that practically does what you're looking for, you can download this model from the marketplace, but you can also actually develop your own model and you can ask for different resources, at least at the moment within the project, but in future then we see open. Yes, and then you have the option to actually try out different things like training and inference. And for example, for one of my models, it looks like this. So you can customize different options depending on what you're interested in doing. And yeah, so this can be very helpful, especially in the future for those of you looking for different resources. Then that is it.